Alrighty, howdy folks. Moving on, chapter 13, section 2. Derivatives of integrals and vector functions. Last time in section 1, we saw just vector functions, kind of like some of the graphs of those things and certain things like domain, limit, and all that, right? Now this time we're going to look at the derivatives and, did I say derivatives of integrals? Crud. I meant to say derivatives and integrals of vector functions. Jeez, come on, Sammy, wake up. Sorry about that, folks. I'll try to fix it. Okay, cool. The derivative r prime of t of a vector function r of t is defined as r prime of t, which is dr dt, and that's just nothing similar to Cal 1 stuff. R evaluated at t plus h minus R evaluated at t all over h as h approaches 0. Do you remember that equivalent in calculus 1? F prime of x. What is f prime of x? Its limit as h approaches 0 of f of x plus h minus f of x over h, right? This is a similar version to it. Nothing big deal. And let's look at theorem. If r of t is a vector function f of t, g of t, h of t, where f, g, and h are differentiable functions, basically you should be able to evaluate the limit, that particular limit of the difference quotient. That's all there is to it. And also, if you recall, when is a function not differentiable? Absolute value of x we know is not differentiable at x equal to 0. Why is that? Because there's a sharp corner. So anytime there's a sharp corner, or another word for that is kink. I don't know what's so kinky about it, but kink. That was a bad joke. I shouldn't have said that. Please forgive me for that. So if there's a kink in the graph, you cannot differentiate the function at that point where there's that kink, right? What else? When else would a function not be differentiable? If there is a discontinuity, any kind of discontinuity, jump discontinuity, removable discontinuity, or infinite discontinuity, the function is not differentiable at that point, right? That's another concept that we learned. Same things appear. Same things are valid even this situation. F, G, and H are just functions of a variable t, and so when we say are these differentiable, then you're simply asking are there any sharp kinks in this one, sharp corners in the graphs of any of these functions, and those kind of questions. All right, moving along. And so basically r prime of t is nothing but f prime of t, g prime of t, h prime of t. What are we saying? Well, you want to find the derivative of this vector valued function. Do one thing, find the derivatives of every one of those component functions f, g, and h, and you're done. That's as simple as that. Will the problems look that simple, man? Yes, they will look very simple. Okay, but there are some interesting concepts, and I hope I can show you those interesting things. Especially I'm going to use Geogebra to show something really cool for you. Okay. The significance of r prime of t is that it represents the tangent vector at the point r of t to the space curve. We looked at space curves in the last section, right? Now, for a space curve, would we be able to draw a tangent at a point? More so, could we draw a tangent vector to that point, to that curve? What's that? I gotta say, at that point to the curve, whenever I talk about a tangent vector, right? And so, okay, now the question may be, who cares what the tangent vector to a curve at a point is? We, especially engineers and physics people too, we care about these tangent vectors quite a bit. And it is for this reason. Hopefully I can demonstrate this to you using GeoGebra, but here is the idea. As t changes, r changes. Is that a fair statement to make? Yeah, man, r is a function of t. So if t changes, r changes. What does r represent? It represents a position vector, meaning at a particular t, r has a certain value. That means it represents a particular position vector. Or if you think of a point at that place, at those x, y, z coordinates, you have a point. And that point keeps moving as t changes. What's the key here? The point keeps moving. As engineers, we know whenever something is moving, we can always talk about what its speed, which would be a magnitude of how fast the point is moving. Or we can even talk about the vector quantity velocity associated with that movement. What would that vector quantity velocity represent? It represents the speed and in which direction the that point is moving. I'll probably use the word particle synonymously with the point. I shouldn't, but it's boy. Please accept that. Okay. So we would like to know in which direction the point is moving or the particle is moving and with what speed. And that is represented by the velocity vector. And it turns out its direction of motion is exactly along the tangent vector. If the tangent vector is pointing vertically up, you can be confident that the particle is actually moving vertically up at that time. And if the tangent vector is to the left, pure left, you can be confident that is the way it is moving at that point. A position, you cannot tell which way a point is moving based on the position. Please pay attention to this part. Let me repeat that. You cannot tell which way a point is moving based on its position. Really? Yeah. If I told you, let's say, hey, a particle is moving along the x-axis. Now, the particle is at x equals -2. Tell me, which way is it moving? It could be moving to the left, or it could be moving to the right. There is no way to tell based on the fact that it is negative. No, man, but because it's at -2, it must be moving to the left. No. Couldn't something be moving to the right, even though it is at a point x equals -2? It could. However, the beauty is this. If I were to tell you its velocity vector is pointing to the left, now you can if the velocity vector is pointing to the left, you can be guaranteed the particle is moving to the left. What about acceleration? Nope. You cannot tell based on the acceleration vector which way the particle is moving. You could have, when you apply brakes, you are moving forward, but your acceleration is pointing backwards. Right? So that's why this tangent vector in a practical case for us engineers is a very important concept. For parametric curves, this whole thing is very simple. So like you saw, how do you find the velocity? How do you find the tangent vector or the derivative, man? Just take the derivative of the components. Done. Okay. And then we need to talk about a unit tangent vector. It's simply because, how should I put it? Maybe I'll put it this way. Good. What's a unit tangent vector? Well, the derivative vector was r prime of t. Divide that by the magnitude of that r prime of t, you got the unit tangent vector. R prime of t itself is the tangent vector. The moment we divide that by its magnitude, we must get a unit vector along that same direction. Right? The reason this unit tangent vector is important is because, okay, if I were to tell you that the unit tangent vector is I plus j, right? Can I say that? The unit tangent vector is I plus, could it? No, I cannot say I plus j. The unit tangent vector, because the magnitude won't be 1. Okay, 1 over square root of 2 times I plus j. Would that work? 1 over square root of 2. I square magnitude is 1 plus 1, and square root of 2, square root of 2. What am I saying here? Come on. If I say I plus j, what's the magnitude of that? Square root of 2. Okay, if I divide that by the magnitude, I should get a unit vector. Damn. Okay, yes, 1 over square root of 2 times I plus j. Let's say I give you that the unit tangent vector when a particle is traveling along a space, in space, is at a point, is this 1 over square root of 2 I plus j. And I tell you that the speed is 40 meters per second. Now, if I asked you, what is the velocity vector? What would you do? Simple. The speed, speed which represents the magnitude of the velocity vector times the unit vector. So in our case, 40 times 1 over square root of 2 times I plus j. Done. See, so to be able to represent the velocity vector, knowing the speed, the magnitude, you need the unit tangent vector. That's one of the things that we need. That's one reason why we need unit tangent vector. And you'll see mathematically itself what the pertinence of a unit tangent vector is. Cool. All right. Next, what's the other one? Rules of differentiation. Suppose u and v are differentiable vector functions, c is a scalar and f is a real valued function. Is the derivative of a sum equal to sum of the derivatives? Yep. Does it work even in vector valued functions? Yep, it does. So the first one property is very straightforward, like that. Second one, is the derivative of a constant multiple equal to the constant multiple of the derivative? Meaning, can you yank a constant multiple outside of the derivative? Yep. You can do that even with vector valued function. 3. Derivative of f of t times the vector u of t. Does that make any sense to you? F of t times a vector u of t. Yeah, basically we are saying f of t is going to be a scalar function and u of t is a vector function. Okay, can you have a scalar times a vector? Yeah. However, notice when we have to find the derivative of this quote-unquote product when it comes to situations where vectors are involved, you got to be just a little careful. What product are you talking about? Just if you're talking about the product where you have a scalar times a vector, that's a simple direct product. Whereas if you have a vector and a vector, hey, the product of two vectors doesn't make any sense. You have to be a bit careful when you say, oh, the dot product of two vectors or the cross product of two vectors, right? That's all I'm trying to say. At least in a simple situation like this, we can apply the regular old product rule, first function times the derivative of the second function plus second function times the derivative of the first function, kind of a deal. Okay, that works like that, even in this case. Okay, what about the dot product? Derivative of a dot product, guess what? That same old product rule applies. The only thing is, instead of saying the first function times the derivative of the second function, we say the first function dotted with the derivative of the second function, plus the derivative of the second function times the derivative of the first function. Cool. So u prime of t dotted with v of t. And the cross product. There's something that you need to be careful about here. Let's see. First function times meaning cross product of the derivative of the second function plus the derivative of the first function cross the second function. Could I say, I don't know, man. Back in calculus 1, we studied first function times the derivative of the second function plus second function times the derivative of the first function. So I'm going to say first function times the cross product of the first function times the cross product of the second function. Second function cross the derivative of the first function. Could I swap them? No, right? A cross B is not equal to B cross A. In fact, A cross B equals negative of B cross A. So let's be just a tad careful. So let's try to remember them as first function cross the derivative of the second function plus the derivative of the first function cross the second function. Okay? That's something that we need to be a tad careful about. Okay, second, what if we had a composite function u composed with f of t? Well, as before, the chain rule applies. U prime of f of t times f prime of t. Cool? Common sense we can apply, but as long as you're just a tad careful about some of these, this especially the fifth one. Did we have to worry about swapping here? Instead of saying u prime of t dot v of t, could I have said v of t dot u prime of t? Oh, that would have been okay, because a dot b is in fact equal to b dot a. Right? Cool. Next, sketch the plane curve with the given vector equation. Find r prime of t. Sketch the position vector r of t and tangent vector r prime of t for the given value of t. Okay, r of t equals cosine t plus 1 I, sine t minus 1 j, and we need to draw these at t equals negative pi thirds. Okay. How should we do this? I think I just went ahead and plotted this stuff in Geogebra. I said curve f of t is equal to curve cosine of t plus 1 comma sine of t minus 1 comma t comma negative, what is that? Negative pi to pi or something like that. Yeah, negative pi to pi. I drew, and automatically it drew this circle for me. Okay, and that's your vector curve. Space is not quite a space curve because it's in 2 dimensions. And now r prime of t is fairly straightforward. Take the derivative of the x component. So cosine t, the derivative is negative sine t. The derivative 1 is 0. So the x component simply became negative sine t. And the derivative of the y component is just cosine t, right? The derivative of sine t is cosine t. Derivative of 1 is 0. And so r prime of t is fairly straightforward. We're done with the part A and part B. Sketch the position vector r of t. Ooh. Any idea how to do that? At t equals negative pi third. A piece of cake. Just plug in negative pi thirds for t and figure out the x coordinate and the y coordinate. And it would lie somewhere on this graph. So, like I said, just evaluate r of pi negative pi thirds. Cosine of negative pi thirds is the same as cosine of pi thirds. Cosine of pi thirds is cosine of 60 degrees is 1/2. 1/2 plus 1 is 3/2, 1.5. So there's that 1.5. And let's look at what sine of negative pi thirds is. Sine of negative 60. Sine of negative theta is negative sine theta. What? Cosine of negative theta is just positive cosine theta. However, sine of negative theta is negative sine theta. So we have negative sine of 60 degrees. Negative sine 60 is square root of 3/2. Negative square root of 3/2 minus 1, that's some value. Okay, so basically negative square root of 3/2 minus 1. I factored out a negative, I added those fractions and blah blah, and we get this. Yeah, cool. So what did we do? We at least figured out what r of t is, or at that t value of negative pi thirds is. What else? And we need to do the tangent vector. So now that we have r prime of t, let's evaluate r prime of t at t equals negative pi thirds, and we get this. Cool. Now, what do we do? Oh, that turns out to be this. Okay. So at 1.5, x value of 1.5, 3/2 is 1.5, and that vector is at a negative, the y value is negative square root of 3 is 1.7, about 1.732 something. So 1.73, 3.7, 1.8, about negative 1.8. Yep, that's where that point is located. That's the position vector r of negative pi thirds. But then notice the tangent vector is square root of 3/2 I plus 1/2 j. Both the x and y components are positive. That's why it's leaning to the right like that. And would you see that? Do you see that visually? That this, in fact, this vector is tangent to that circle at that point? That's the idea. Cool. All right. Problem. I'll show you the GeoGebra thing at the end. Find the derivative of the vector function. I'm sure you'll be irritated with me. This is a ridiculously simple problem. You know what the derivative of e to the negative t is? Negative e to the negative t. T minus t cube, 1 minus 3t square. Natural log of t, the derivative is 1/t. End of the story. Okay. What about the derivative of this vector function? Oh boy. Do we know how to differentiate sine square of at with respect to t? Yeah, piece of cake. Chain rule, 2 times sine of at times cosine of at times the derivative of at, which is a. So 2a sine at cosine at. Would you agree? Similarly, t times e to the bt. Oh, you better apply product rule. T times e to the bt times b plus e to the bt times 1. Cosine square ct. Ooh, 2 cosine ct times negative sine ct times c. Just a little difficult, but nothing big deal. Would you agree? That's your r prime of t. All right. What next? Ooh. So this position, this vector function r of t is actually a plus tb plus t square c. So the idea here is a, b, and c, the vectors, they should be treated as constant vectors. That's the key. A, b, and c are constant vectors because r of t, when we say, it's a function of just the variable t. And because nobody said what a, b, and c are as functions of t, we should take it as constant. We should take them to be constant. And ridiculously simple, the derivative of a constant vector is 0, derivative of a is 0, derivative of t times b, b is a constant, so derivative of t is 1, c is a constant, so derivative of t squared is 2t, end of the story. Right? I hope you didn't feel insulted by my doing these problems. I did that just for sake of completeness. Cool. All right. Oh, we need to take. All right. Find the derivative of the. This is interesting. Find the derivative of the vector function r of t equals ta crossed with b plus tc. Do you remember ta? So should we say ta times the derivative of this plus the derivative of ta times b plus tc? Yep, ta times the derivative of this plus the derivative of ta time cross b plus tc. Okay, ta, the derivative of b plus tc, derivative of b is 0. C is a constant, so that just becomes c. So we have ta crossed with c. That's exactly what I have as the first term. Plus ddt of ta, that's just a is a constant vector, so we have just a. So that's what we see here. Cross this b plus tc, we just write it the way it is. And the thing is, now if you notice, we can write this as t times the quantity a cross c. You can always factor out the scalar t and write like this. And then we have a cross b, right, plus a cross tc, and the t can be pulled out, and t times a cross c. Lo and behold, we have a t times a cross c here, and also another t times a cross c here. Let's add them up to get 2t. I didn't do that? Oh, lordy. I think it'll pop up at the end. Okay, so basically it is in fact 2t, 2t times the a cross c plus a cross b. Okay. All right, find the unit tangent vector t of t at the point with the given value of the parameter. We need to find t prime of t at t equal to 0. In other words, we need to find not t prime, sorry. We need to find t of 0. That's what we need to find. The unit tangent vector t, but at t equal to 0. I got a good question for you. To find t of t, that unit tangent vector uppercase t, vector t, do you remember I said you do r prime of t over the magnitude of r of t, right? R prime of t over magnitude of r prime of t. That's how you find the unit tangent vector t. So to find t at 0, pay attention to this. To find t at 0, could we do r prime of 0 over the magnitude r prime of 0? And to find r prime of 0, can we find r of 0 and differentiate it? The answer to the first part, that is, can we find r prime of 0 and then divide that by magnitude of r prime of 0? Yes, we can. But the second part is false, which is to find r prime of 0, can we find r of 0 and differentiate that? That's a no-no. What? Yeah, check this out. Let me take you back to calculus. If I said, hey, f of x equals x squared, find f of 3 for me. What do? You'll say, okay, f prime of x is 2x, and f prime at 3 is 2 times 3, which is 6. That is okay. But could you say, What? You want f prime of 3? Okay, man. F of x equals x square. So f of 3 equals 3 square, which is 9. And the derivative of 9 is 0. You cannot do that. You wouldn't do that, right? That's the thing that I wanted to point out. So in order to find t at 0, if we want to find r prime of t first, and then evaluate it at t equal to 0 to get r prime of 0, that's okay. And then divide, of course, by the magnitude. That's going to be our strategy. So r prime of t, oh, by the way, yeah, what's the derivative of tan inverse of t? 1 over 1 plus t square. And what's the derivative of 2e to the 2t? Simple, 4e to the 2t. And then here we apply a product rule to get the derivative of 8te to the t. 8 times t to the t plus e to the t. So that's r prime of t. Now that we have found r prime of t, to solve our problem, if you want to find r prime of 0, yeah, that's fine. And so that turns out to be 1, 4, 8. And how do you find t of 0? Well, simple. R prime of 0 divided by its magnitude. I should have had a vector sign there. Magnitude of r prime of 0. Okay, so 148 over 148, and that turns out to be this vector. Does it make sense that the unit tangent vector is in fact a vector? Yeah, it does. And also, what else should you verify? Let me put that in the form of a question. Is this the unit tangent vector? How do you check that? You check that by finding the magnitude and making sure that that magnitude is equal to 1. And the answer is, yeah, of course, duh. 1/9 square plus 4/9 square plus 8/9 square. What's that going to be? In the bottom, you will have a 9 square, and the square root of that. In the bottom, you have a 9 square, whereas 1 square plus 4 square plus 8 square would be 1 plus 16 plus 64, turns out to be 81. Square root of 81 is 9, and 9 over 9, ta-da, that is in fact equal to 1. So yes, this is a unit tangent vector as it promises. Okay. See, I told you. Stupid. Why am I such an idiot, man? Okay. R of t is this. Find r prime of t, t of t, r double prime of t, r prime of t dotted with r double prime of t. I think this is a silly simple problem. You just keep finding all this nonsense. Take the derivatives and then take the you get r prime of t, r double prime of t. Just patiently work that out to get t of t, r prime of t. Vector. So you do that, and then what? What the hell am I doing here? I'm trying to find the magnitude of this. I think the problem statement actually says in the book where I copied this problem from, it says do this, I think, at some particular value of lowercase t. Yeah, but that's okay. I just went ahead and did the big long thing, factored out a few things. I don't know. Okay, some big long thing. So that's your t of t. It would have been so much simpler if I had found t of just some 0. Could have figured out r prime of 0 and divided that by the magnitude of r prime of 0 and be done with it. So that turns out to be that. And yeah, the dot product. You know how to find the dot product of two vectors. Whether they are two vectors or two vector valued functions, the idea is simple. A dot product is multiply the like components and add them up. That's the dot product. Okay, what else? Find the parametric equation tangent line to the curve of your specified point. Oh, okay. Take a look at this. So they have given us the component functions of this one, and that is x of t, y of t, and z. And they have given a specific point at, this, oh, by the way, yeah, this is a good one. Check this out. There's something very interesting in this and we need to find the tangent line to the curve. What is that? The parametric equation of the tangent line to the curve. Whoa, so this is bringing back stuff from the previous chapter. Tangent line. Try to recall what it is that we need to know to express a line as in its parametric form. What's the parametric equation of a line? You remember that from the previous one? Okay, I'll remind you. And there's something else that's interesting. What is that? So, our strategy is to first find r prime of t and evaluate it at the given point. What? To find a tangent line to the curve, we need r prime of t? What has r prime of t got to do with a tangent line to the curve? Everything. Right? The tangent vector is in fact tangential to the curve at that point, and tangent vector is related to r prime of t. The unit tangent vector is r prime of t divided by the magnitude of r prime of t. Yes, so we do need to do that. This gives a vector that is parallel to the tangent line at that point. Stop there. Pause the video and listen and read that point carefully. When we find r prime of t, this gives a vector that is parallel to the tangent line at that point. Is that true? Yes, it gives us a tangent vector, which is nothing but parallel to the tangent line. In fact, when I say parallel, it falls right on top of it in this case. Okay, and what else do? We will then use the concept in the previous section, or previous chapter I should have said, that given a point on the line and a vector parallel to it, we can find the parametric equation to that line. Isn't that true? Back in previous chapter, in order to find the equation of a line, we need two things. The coordinates of a point of any point on that line and another vector that is parallel to it. Do we know a point on the line? Yeah, this 2 natural log of 4, 1, that is the point. So we're done. The only thing is we need to get parallel vector, a vector parallel to that line. And that's exactly what we are going to do by finding r prime of t and evaluating it at this point. Cool? Just allow that whole thought to sink in. All right, r prime of t, I took derivatives of each of these functions. Square root of t squared plus 3, 1 over 2 times square root, do that and you get this. Natural log of t squared plus 3, 1 over t squared plus 3 times the derivative of t squared plus 3 is 2t. And the derivative of t with respect to t is just 1. Right? R prime of t. Now, here, absolutely pay attention. Can you find r prime of t at our point? What's our point? The point is 2 natural log of 4, 1. Wait a minute. What are those things? 2 natural log of 4 and 1? What do they represent? They are the x, y, z coordinates of the point. Right? They are the x, y, and z coordinates of the point. Okay. What do we need to find r prime? We need t. But we don't know what t at the point is. All we know is the x, y, z coordinates of the point. Would you agree with me? But then the question becomes, given the x, y, z coordinates of a point on this parametric curve or the space curve, can we find what the corresponding t is? Up until now, what happened is we are given these component functions as functions of t, and we are given a certain t value, and we say, for example, hey, can you figure this out when t equals 2? And you say, hey, piece of cake, man, plug t equals 2, and so square root of 2 square plus 3, and that's your x coordinate and y. We can figure that out. But here, we have to go the opposite way. We are given x, y, and z, and we need to find t. What? How do you do that? Simple. Obviously, square root of t square plus 3 must be equal to 2. If I tell you square root of t square plus 3 equals 2, would you be able to solve for t? Piece of cake, man. Square both sides and you get t square plus 3 equals 4. And subtract that, and t square equals 1 you get. And so t equals plus or minus 1. Right? What's the big deal about that? Yes, we can pick any one of these things, set it equal to the corresponding coordinate, and solve for t. But let's be a little careful here. When we got t squared to be 1, t could have been either positive 1 or negative 1. Which one should we use? Oh, it doesn't matter, man. Oh, really? If I take t to be negative 1, is z satisfied? Z then becomes, by virtue of being equal to t, negative 1. Is that the z coordinate? No, z is 1. So, in fact, we could have been much more judicious and said, wait, z equals t, and according to this, z equals 1, therefore t must be equal to 1. Can we use that logic? You bet you can. Right? T equals 1. But then let's check. Will that satisfy both x and y? When t equals 1, we have 1 square is 1. 1 plus 3 is 4. Square root of 4, right? Square root of 4 is just positive 2. Yep, that is true. What? Did I say square root of 4 is only positive 2? Isn't square root of 4 plus or minus 2? No. Square root of 4 is just 2. However, check this out. If t square equals 4, then t could be plus or minus 2. That's a different thing from saying square root of, what is square root of 4? Square root of 4 is only positive 2. In fact, square root of x square is absolute value of x. Okay, I don't want to go into that much. What are we saying? Okay, 1, t equals 1. So when we plug 1 for t here, we get 1 square is 1, 1 plus 3 is 4, and we get natural log of 4 to be y. Is that the chord? Yep, that is it. So we are given the point of what are these different values? They are the x, y, z coordinates, but we need the corresponding t. How do we find it? So like I said, z equals t equals 1 is a simpler idea, and it checks out because when we evaluate x of 1 and y of 1, we do get 2 and that. So r prime of 1, r prime at a 2 natural log of 4, 1 is the same as r prime evaluated at t equals 1. And that's our parallel vector v, which is ABC. And the point itself is this x, y, z. So this is what I'm saying is p sub 0, x 0, y 0, z 0. And do you remember? what the parametric equation is? So the equation of line is x equals x sub 0 plus at, and we know a is equal to 1/2. Just use that and we're done. Cool. That's somewhat of an interesting problem. All right. What else? Ooh, definite integral. The definite integral of a continuous vector function r of t can be defined much the same as for real valued functions. The resulting quantity is a vector and you just integrate them. And I didn't even bother to solve a single problem based on that because that's so silly. If you know this, how do you integrate a vector valued function? Oh, integrate each of those component functions separately and put them in the form of a vector. Yeah, duh. Right? So I'm not going to, oh no, I did do an example. What happened here? No. They look a certain way, and I told you already. I'm not going to bore you with the repeat explanation of all the crud that I do. Okay. Where are you? Hey, is the audio quality any better? I'm using a Blue Yeti mic, man. This is pretty cool. But it's sticking right in front of my face. I couldn't even see the laptop. Anyways, integral 0 to pi 4 secant t tangent t I. Okay, the only big question in this one is, do you know how to integrate secant t tangent t? Yeah, that's just secant t, right? Yep, secant t evaluated from 0 to pi 4. Ta-da! T cosine 2t. Integration by parts. U equals t, dv equals cosine 2t dt, da da da, and you do all that nonsense. And then evaluate it, apply the limits, and you got this. I'm not going to bore you with this, guys. Okay, how about sine square 2t cosine 2t? U substitution. U equals sine 2t. Then du equals... I'm a great guy. I didn't even bother to show you all of that. U equals sine 2t, right? That's how you can solve this integral. Do a u substitution. U equals to sine 2t, so du equals 2 cosine 2t dt, and so 1/2 sine cube 1/2 u square du. Yeah, 1/2 u square du, and 1/2 u cube over 3, which is 1/6 u cube, and u we said was sine 2t, so this became sine cube 2t, evaluated from 0 to pi 4. Sine of 2 times pi 4 is sine of pi half. Sine of pi half is 1. Sine cube of pi half is 1. This is 1/6. Sine of 0 is 0, and so minus 0. 1/6 minus 0 is 1/6. That's all there is to it, guys. The integral is, like I said, express it in a vector function. All right, with that, I'm going to take you to Geogebra and show you something really cool. So here's a vector valued function. X equals cosine t, y equals sine t, and z equals cosine 2t. Right? So when t takes on a value of 0, that represents this point. Cosine 0, sine 0, and cosine 0. So 1, 1, 0, 1 is this point. And if I run the animation on this, you will see that the point moves like that. For different values of t, it occupies different positions as indicated by this. So, great. What is important is, what about the tangent vector? can we figure out the tangent vector? And that's what I'm doing here. So once we have the vector valued function, we can find f prime, r prime, and then for the unit tangent vector, as before, divide by the magnitude. And I drew that vector here. And check this out. If I run the animation now, that vector stays perfectly tangential to the curve. Constantly it's pointing towards the tangent in the tangential direction. Okay, cool. Ta-da. Man, that would be a wonderful roller coaster. Okay, now yep, if you take dynamics, you will see that, and probably in physics you'll see this too. Let's say this is in fact a roller coaster, and let's not put you in the roller coaster. They're doing a testing, let's say, with nobody in. It's a new roller coaster, newly designed one, and they're doing a testing. And it so happens that when the roller coaster is at this, when the car is, say, when the what? You're not letting me move that? When the okay, so when that position, God forbid, the thing snapped, which way will the car fly? And the answer is whichever the direction of its velocity is, whatever the direction of the velocity is. What is the direction of the velocity as it is moving? That is along this tangent vector. So it will in fact literally take off like that. Of course, because of gravity, it'll get pulled down. But if that were to be the only force acting on it, then it would in fact take off in that direction. And similarly, if it were to be there, it will fly off tangentially at that point. So this stuff is pretty useful, folks. Cool. Well, that's all I wanted to talk about today.